Hi, this is Michael Bliss from the Village of Walden Recreation and Parks Department. Thanks for joining in on our 7-part online recreation experience running every Wednesday 11 a.m. through the end of August. I want to send a big thank you to the late great John Shardulo and the Shardulo family for making this opportunity possible for the youth of our community. Please share on your Facebook and spread the word to all the kids in our community so they can get involved in the fun. Enjoy the show.
Hi, my name is Eric. I'm your local mad scientist. I want to thank you guys for joining me in the Mad Science Lab today, and hopefully we'll have a good time. Before we get started, though, normally there are 3 rules of mad science. Today, there's really only one. The one rule of mad science is you have to have fun. Science is meant to be fun, so I'm going to try and make that as fun as possible. Now, every time I go somewhere, I'm always asked the same question, and I don't understand why I'm asked it. People say, "Are you going to do magic?" Well, here's the thing. I'm not a magician. I'm a scientist. The thing is about magic, though, is magic is really just using science. And so what I'm going to do is I'm going to start off with a science/magic trick. Some of you might have seen it before. Some of you haven't. It's still a lot of fun no matter what. Now, if you've seen the trick where they have 3 cups, they put a ball underneath one of the cups, and then they mix them around really, really fast, and you have to follow the ball. Well, this is similar to that. So what I'm going to do is I need your best staring face. This is a staring face. Now, very important, you have to watch the cups. Now, I'm going to change it. Instead of using a ball, I'm going to use water. And I'm going to take water from this beaker and pour it into that cup. Now, before I go on, make sure you keep your eye on this cup. I'm going to mix them up really, really, really fast. And you have to watch, and I'm really good at this. So let me warm up a little bit. Okay, good. Watch the cup. I'm going to go incredibly fast. 1, 2, 3. Okay. Now, I know that might have been a little too fast, but I need you to pay attention. I want you to think about it, and you're thinking about it in your head. Make sure, do you think the water is in this cup? Probably not. Raise your hand if you think the water's in this cup. No, not that one either. The water, think about it, is the water in this cup. It absolutely is. And you guys are really good at this. That wasn't too fast, I guess. So I'm going to take the water from this cup, pour it into this one. Now, this time, I'm going to move even faster. Now, I know you're thinking, Eco, there is no way you can go faster. But I can. You have to keep your eye on that cup. Let me see your staring faces like this. Make sure you're don't look at me, look at the cup. The cup moves, I stay here. Here we go. I'm going to go even faster this time. 1, 2, 3. And one more time. Okay. Raise your hand if you think you know where it is. All right, well, that was faster. You guys are pretty decent. I'm going to take the water now. I will take it, and I will pour it into this one. Now, again, really fast. Keep your eye on the cup. Best staring face. Don't let anything distract you from staring at this cup. Make sure you're watching it at all times. Very important. Here we go. Watch the cup and watch the cup. Keep your eye on the cup. Watch 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 the cup. Good. Now, is the water in this cup? Do you think the water's in this cup? Or do you think the water's in this cup? Well, okay, not bad. Some of you got it. Some of you might have lost a little bit, but it's fine. So I'm going to take the water from this one, pour it into this one. Now, again, remember, nothing distracts you from looking at the cup. I'll move it there so it's easier for me. Here we go. Watch the cup, keep your eye on the cup, keep your eye on the cup, watch the cup, watch the cup, keep your eye on the cup. It's still moving, it's moving, I'm moving. Keep moving, cup, there. Okay, now think about it. Raise your hand if you think the water's in this cup. Or think about it, where do you think the water's in this cup? What about this one? Well, what we're going to do is we're going to test to see if you have a good idea of where the water is. So if the water is in this cup, if I turn it over, all the water from this cup will fall right on the table. So we'll test it. Here we go. 1, 2, 3. No! Huh. No, not there. All right, let's test the one in the middle. If I hold it up like this, now what you're doing is you're coming up with guesses. You're coming up with a hypothesis, what you think will happen. So if I take this cup and I dump it upside down, 1, 2, 3. Huh, not there either. If I take the last cup, by process of elimination, we have to think it's in this one. So we're going to test it one more time, but I need you guys really, I don't want my table to get a mess. So here we go. 1, 2, 3, and I dump it. Well, all the water came out and it kind of changed. Now, what I did is I put a powder in there. I put a powder in there that soaks up 100 times its own weight in water. That powder is called polyacrylate. I call it slush powder because it's just easier to remember. So if I take some slush powder, I put it on the bottom of the beaker here. And what I'm going to do is I'm going to see how long it would actually take to soak up all that water. So if I take the water from here and I dump it in here, I'm going to see how long it takes. Now, I want you to think about how long you think it would take to soak up all that water. So if I take the water, I put it in here. Now, make sure you're ready to count. And go. 1, 2, 3, 4, 5. It takes about 4 or 5 seconds before all the water becomes this. Now, this is a lot of fun for magic tricks, but why would scientists come up with a powder like this? What could you use it for? And everyone has used it before. What if I told you they put it into a diaper? I know that's kind of gross, but have you ever seen a baby or a toddler at the water and they put them inside the pool or inside at the beach and they come out, their diaper's like this big and they're moving around like this, they're kind of waddling. Well, what happens is the powder is inside the diaper. So as that liquid tinkle is going all over, it keeps the tinkle from going down the leg. It absorbs the water. And what we're talking about today is we're really talking about how things react. Right now, the water reacted to the powder by getting soaked up like a sponge. Well, not everything reacts very, very differently. So I'm going to take out one of my favorite things. And before I take it out, I actually have to put a glove on my hand. And I have to use that because I need to protect my hand. Now, think about it. Have you ever taken an ice cube and held it in your hand before? Yeah, is that ice cube so cold that you need a glove? Or when you put it on without, if you hold it without a glove, you freak out and you're like, ah! Yeah, well, it's not that cold. See, water freezes at a temperature of 32 degrees above zero. Not that cold at all. And water is one of those few things. It can be 3 of the 4 states of matter. It can be a solid, it can be a liquid, and it can be a gas. It can be all 3. When it's frozen, it's a solid. When it melts, it becomes a liquid. And then when you heat that liquid up, it becomes a gas. It can be all 3. What I have with me today, one of my favorite things, it's a little different than that. See, this, some of you have seen it before, some of you haven't. This is called dry ice. Now, that is a really weird name to call something, to call it dry ice. And it's called dry ice for a reason. See, you already know that ice was made from water. This is not made from water. In fact, when you breathe in oxygen, but when you breathe out, you're breathing out carbon dioxide. And that's what this is made of. It's a frozen gas. I'm even going to come around so I can come a little closer. It is a frozen gas. And it is so cold that the coldest day this year was probably 10 degrees below zero. This is almost 100 degrees colder than that. If I blow on it, it's changing into a gas very, very quickly. This is so cold. If I didn't have the glove on, I'd freeze my skin. I'd get something called a cryogenic burn, and it happens in seconds. even through the glove. In a little while, I'm going to have to put it down because it'll start getting really, really, really cold on my fingers. But I can do a couple things with it first. Now I'm going to take out a very scientific tool, can be kind of dangerous, still pretty awesome, but dangerous. You need to be careful with it. In fact, let me put my goggles down. Very dangerous metal spoon. This is very dangerous. You know what? Oh no, that's not dangerous. Oh, I get confused. Well, if I take the spoon and I put it down on the dry ice, see the spoon is really, really warm. The dry ice is very what? Cold. So if I put the spoon down and I force it down on the dry ice, you're going to say, oh, that was disgusting. Excuse me. It kind of sounds like a toot. It's what it does. If I force it down really hard, even gets a little squeaky. Now, if I just put it down, you might be able to hear it. It kind of sounds like a bell. And what's happening, again, is the spoon is really, really warm, but the dry ice is very, very cold. So the gas, the carbon dioxide, is pushing on the spoon. Now, if I take a larger spoon, I'm wondering if it would change the response of the dry ice, the reaction. So if I put the larger one down, a much larger sound. There's more area for the spoon. And again, forcing it down and all that gas wants to escape. It wants to spread out. If you stop it from spreading out, it always looks for a place to get out, a weak spot. So right now it's on the edges of the spoon. But if you really force it down, you have other reactions that will actually happen. Now, again, I have to put the dry ice down because it gets cold even through the glove. And I can even feel it on my fingertips. It's cold really, really fast. So what I want to do is I want to see how this actually reacts to other things. Because I'm asked all the time how long this will take to melt. This will never melt, ever. If something melts, it turns from a solid into a what? Yeah, a liquid. This will never turn into a liquid because it was never made out of a liquid. It turns into a gas. There is another word for that. They say it will sublimate. If something sublimates, it turns from a solid to a gas. If it evaporates, it turns from a liquid to a gas. And if it melts, it turns from a solid to a liquid. This doesn't turn into a liquid. So if I left it out for a while, it would actually sublimate. Probably that whole piece would probably sublimate maybe 2 or 3 hours, and it would be completely gone. All that gas would spread out around. Now, if I take it and I try to add it to something a little different, so I'm going to take my beaker here, and my beaker has nothing but warm water in it. So if I take some pieces of dry ice and I put it in there, start to think about what the reaction would be. And this is pretty warm water. So I'm going to reach over here, grab some small pieces of dry ice. There we go. And if I take it and I add it to my beaker, this again just has warm water. Kind of curious what'll happen. Now remember, I want you to come up with your own hypothesis, your own guess what you think would happen. Could explode. It could just freeze. Well, let's see. So if I take a lot of dry ice, see, when it does this, I love it because then I get to go like this. I go, like a little bubbling potion going on here. And anytime you've seen a movie that has bubbling potions, this is what they're using. They're using dry ice because it does give this kind of reaction. And all that's happening is it's turning into a gas very, very quickly. I'm going to come a little closer so maybe you can see it a little better. If I take it right over here, you can see it's actually just changing into a gas really, really quick. And the gas that's coming out, it's not going up. It's actually more going down because the gas is heavier or more dense than the air. So it goes down. If it were less dense, it would go up, just like inside these balloons. The gas is less dense, so it floats. So again, anytime you've seen a movie this is what they're using. And I can show you, it's really not the gas itself. And you breathe it out all the time. I can even take it, put it on my head. It's nice. I can't see though. And as you can see, it's actually not even coming out as fast as it was before. It's slowing down. And what's happening is the water is getting colder. There's less dry ice, but more importantly, the water is getting colder. Now, again, I'll come a little closer so you can see it bubbling underneath. I'll go around my table. If you look on the bottom there, that's the pieces of dry ice. And those bubbles is all that gas that's coming out to go out, to escape, to spread out. But again, it is slowing down. Now, if I change the container, it's absolutely going to change the reaction. So what I'm going to do is I'm going to take this. Now, this is one of my mad science potions. And you guys have one job to do. Your job is to make sure you watch the pink. Make sure nothing happens to it. Okay? You got to make sure it stays there. I'm not going to watch it because I have other things to do around here. But I'm going to reach inside here. Are you guys watching the pink? Don't take your eyes off the pink. It's one of my favorite colors. All right, so I'll come over here. I'm going to grab some small pieces of dry ice. And again, just keep your eye, and I want you to observe. And observation is just what you see. So you have to realize and think about what you see. So if I take a couple of pieces of dry ice, I'm going to put it in here. I need a smaller one than that. Keep your eye on the pink. Make sure nothing happens to it. There we go. Now, wait, that's not pink. I asked you guys to watch it. Make sure nothing happens to it. I don't like it when it's that color. So let's get the pink back. So I'll take this chemical. That's awesome. All right, so now I have my lovely pink back. So you have that great color pink. And the reaction is the same as when I put it in here. And again, make sure you watch the pink. Make sure it doesn't go anywhere this time because I really like it there. All right, perfect. So let me reach over. Excuse me. I'm going to get more dry ice over here. You guys watch the pink. Nothing. So we'll take it. And if I look again, now what happens is I put a chemical in here that can tell me if there's carbon dioxide in the water. What does it do? What is the change that lets me know? It's a color change. And it went right from pink to clear. It's just letting me know how much carbon dioxide is actually in the water. All that carbon dioxide that's coming out, filtering all around. In fact, what was regular water is now becoming seltzer. It's becoming bubbly water. The same stuff that makes soda fun to drink, those bubbles, that's what it's putting into the water. Now, if I change the chemical, I'm wondering if it would change the reaction. So I'm going to change it to this one. Now, this one is kind of like a deep purple. And I'm going to reach over here. I want you guys to keep in mind what happened to the other one. There we go. And come up with your own hypothesis. What will happen to this one? Now, sometimes you actually can make a hypothesis and say, I don't think anything would happen. That is a guess. But if this one went from pink to clear, you've got to think, is this one going to go from purple to clear? Is it going to change other colors? Is it going to explode? Which would be awesome. But let's take some pieces and keep your eye on this one. In fact, I'll come a little closer again. Maybe we get there we go. Look at that one right here. I'll take some pieces of dry ice, put it in here. And I need you to watch to see if there's a difference between this one and the first one. I really don't see it. So I'm going to put it down right there. I have my lovely deep purple. I'm even going to add another piece of dry ice to that. So you see the gas come out. I have my lovely purple. Now, oh, that's like a tealish green. Okay, I can deal with tealish green. So I have my tealish green potion, which is kind of awesome. Let's take another, that's getting like an ugly color, yellowish green. If I put another, ew, that's getting awfully close to like pea yellow, which is kind of nasty. So if I come over here so you can see the difference, I'll come back up to the front and show that. It definitely changed. It's actually even getting closer to orange now. And what happens is I have a different chemical in there So there's a different reaction. And I want you to think about it. What was the difference between this one and this one? This one went right from pink to clear. This one had multiple changes. It went from purple to like a bluish teal to a green to pea yellow, and now it's like orange, which is much better than the pea yellow. If I take my chemical and I add this and I add more hydrogen to that, I'm going to get my purple back a little bit, but it'll keep changing as long as the dry ice is in there. It'll keep going back. So there's the difference in that reaction. So it's going to change. The reaction is going to change depending on the container or even what chemical is inside. Now, anytime you see a chemical, and I did start with this, and usually I say it in the beginning, even though you think you might know what the chemical is, you have no idea. You might think it's water, but it's not. So it's never very safe to test it by putting your hand in it or tasting it. You can come up with a guess. I think it might be water, but you'll never know for sure. This chemical that I put in here, probably one of the most dangerous chemicals I use. If you were to taste it, you're not going to feel very good at all. I'm going to change the container and see if the reaction is any different. And this show is called Fire and Ice. So most of it is on the ice, but then we'll get to a lot of the other stuff later. So I'm going to take this container. Now this is called an Erlenmeyer Flask with a sidearm. It's got a cute little sidearm right over there. I'm going to take some pieces of dry ice. I'm going to put it into this one. And I want you to think, it has a way for the gas to come out there, and it has a way to escape from the top. So I'm going to take some dry ice, put it into this one, and I kind of want to trap that gas inside. I don't want it to escape. So if I hold it up like this and I cover the top, you go, oh, well, that's interesting. If I turn it to, oh, wait. Oh, that's good. I'm going to do it again. Hold on. Kind of tastes like a soda burp. It does. Because it tastes like a soda burp. Because this is the same stuff that you put into soda to give it the bubbles. That's what makes it fun, is those bubbles. And that all those bubbles are is carbon dioxide. So if I take it, and sometimes you can even come out of my nose and say, that's good. But if I really do want to trap it, I might want to take a smaller one. I'm going to take this smaller one right here. I'm going to empty some of that there, a little too high. I'm going to take some smaller pieces. I'm going to put it into this Erlenmeyer flask with a sidearm. Put my goggles down a little bit. I'll reach inside here, grab some small pieces. There we go. Take my Erlenmeyer, put the pieces of dry ice in there. Awesome. So now it's coming out very quick if I trap it. So if I take this stopper and I put it on top, there. So now it can't come out. Perfect. So oh, it could come out there. Let's seal it here. You have all that gas. Whoa! Hold on, wait. Stopper on the bottle. There we go. See? Ah! Wait, stopper on the bottle. There we go. See? Ah! Yeah, the stopper won't stay on the bottle. And I want you to think about why. What is happening? See, all that gas wants to spread out. If you stop it from spreading out, it's always going to look for the weakest spot. Right now, the weakest spot is by the stopper. Now, I can't do it. But what would happen if I sealed it here so it couldn't come out, and I sealed it here so it couldn't come out? What do you think would eventually break? The glass. That's how strong the gas actually is. Always going to look for that weakest spot. If you take a soda can, shake it up, and then open it, what happens? Yeah, you have the explosion. You have all that soda and the bubbles coming out of it. All that is that carbon dioxide, that gas escaping really, 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 really quickly. Now, if I do want to trap it, I'm going to move some of this stuff over so we have a better view. Move that out of your way. Let's get this one out of the way and this one out of the way. I'll leave the other two going. What I'm going to do is I want to trap it in something a little different. I do need this one. And I'm going to take, let's go with this container. Now, this is a little different. We have a long tube coming up here that's hollow, and I have a tube, plastic tube that comes right out from under it, right up from the top. So I'm going to take some pieces of dry ice. I'm going to put it in here, and I'm wondering if it's going to change how the gas looks as it comes out. So I'll reach inside my bag over here, grab some pieces of dry ice, put them in here. There's 1 and 2. Awesome. If I take this and I put it on top, so now, ooh, it's coming out there. So now I can actually take a mad science shower, which is kind of awesome. Get my shirt there. That's nice. All right. If I take, though, something else and I put this in here, I'm kind of wondering if I could trap it. Whoa. Now I have the gas trapped in bubbles. And that's all it's doing is it's trapping it inside the bubbles. Let's take a little bit there. Nice. So I can put a little bit on my head. There we go. That's not. Ooh. Let's take that. Awesome. We'll take a little bit more. Oh, I'm even going to come a little closer so maybe you can see it a little closer up. So I'll put it over here. Let's get some of that. Nice. And all that's happening is you're seeing a lot of the gas trapped inside of a bubble. And it's going to keep doing that as long as it has something to trap it in. The bubbles get even a little bigger. And you have all that gas trapped inside the bubbles. If I make it come out faster, I'm going to try a different one. I'm going to take this. Now, this is a boiling flask. It has 3 chemicals inside. The first is just water. The second is a chemical none of you have ever heard of or used before. It's called, wait for it, soap. I know, you guys have never used soap. I get that, I understand. And the last is just food coloring. So come up with a guess, your hypothesis, what you think would happen if I add dry ice to this. Now keep in mind, anytime you make a guess, don't ever worry about being wrong. That's what a guess is for. Sometimes they're wrong, sometimes they're right. But that's how we learn. So never be worried about that. So I'm going to take, again, some smaller pieces of dry ice. Let's put it into this. And again, it's water, food coloring, and that mysterious chemical called soap. Let's take some of that, put it in here. So now you can see if I take it, nice. So you have all that gas again trapped in a lot more bubbles. So if I gather it up here and I break the bubble, you can actually see it come right out of the bubbles. Now again, this is how mad scientists take showers. It's very important to stay clean. You put a little bit on my head there. There we go. Take a little bit more. Oh, that's pretty. A little bit more. I'm going to come a little closer so you can see the bubbles again. I'll come right up here. And again, you just have all those bubbles with the gas trapped inside. And as long as the piece of dry ice is in here, it will keep coming up. I'm going to see if I can take it. It gets really hard. It gets hot in here. So this kind of cools me off if I give myself a little crown. Oh, that's nice. I like that. Hold on, wait. I can even go backwards, give myself a little mohawk. I don't know. I can't see. Oh, I look good. With goggles down. Nice. Now, this I definitely don't want to taste. People say, oh, can I eat it? Well, that's kind of a life decision you have to make. It's just soap. I don't think you want to eat soap. But again, it's happening. It's just coming out very quickly. And you can see it start to slow down. But water has these great properties and allows it to actually bond with itself, which is why we actually get the bubbles along with the dish soap. Now, if I make it come out a little faster, what I'm going to do is I'm going to take a different container. And this one I might be able to do twice. We'll see what happens. I have my bucket. Now, this is a bucket full of warm water. A lot of water in there. Trust me, water. I'm going to take a lot of dry ice and I'm going to put it inside this bucket. Now, I want you to make sure, keep an eye on the bucket. I'm going to add a lot to it. As a lot of times people say, add all of it. If I add too much, the water gets really cold really fast, but I'm going to come pretty close to adding all of it. you can see on the bag, see that white? Oh, that's all the frost coming off because it is so cold. So I'm going to take this over here, take a lot of dry ice and put it in here. Now, I want you to think, have you ever seen a scary movie before? You have? Some of you have, some of you haven't. Or a scary movie where they have a fog all on the floor. I always wondered about that. In Scooby-Doo, I know they use ghost fog, which is really the same idea, except that's cartoon. So let's take a lot of dry ice. I'm going to put it in here. And again, I have 2 of these, so hopefully I'll do a second. Let's add it to this. Now it's coming out really, really fast, and I really get to go. It's like bubbles, bubbles, boils and troubles. I feel like one of the witches in Hamlet. But you have all that gas coming out really, really quickly, and it's filling up the mad science office. So you don't see it coming up because it's not that light. It's actually fairly heavy. It's dense, so it goes down. If I tip the bucket a little bit, see it going down really, really fast. And if I take it out, you can actually even see it in my hands. If I take it, I dump it out of my hands. So that gas is coming out really quick. And the water that was in here, that was pretty warm, is getting pretty cold. And that's really what's happening. So hold on one second. It is starting to slow down. So I want it to slow down because then I can try something different. But the water that's in here, as it gets colder, what happens to water as it gets too cold? It turns into ice. And eventually, you're going to get ice on the bottom here. Now, I don't know if you can hear it from there, but if you're quiet, you can hear the bubbles. So listen. I'm going to even move it closer, so maybe it'll be a little easier. So I'll come over here. There we go. Oh, I'll move it down so you can see a little better. Can't see through the fog. So it's really, listen to the bubbles. That's all that gas trying to escape. That's all that's happening. And the colder it gets, or the higher pitch that sound gets, it means it's getting trapped in ice. If I blow on it, kind of see on the bottom. If I reach inside, you're getting ice around the dry ice, but that's really cold. It was fairly hot. Do you guys want to see that again? Yeah, I want to do it again. So I'm going to put this down over here. I'm going to take another bucket. Let's put it right up here. There we go. I have more dry ice in a bag here. And let's see what happens when I do it to this one again. Hold on. Oh, it's a little bit more dry ice, so I wonder what the reaction will be. Let's try. So I'll take that. It should get down to the bottom. You even have the water sprinkling out a little bit. And it settles. It goes all down on the floor. So it looks like there's a fog in the mad science office right now. Nice. Now again, we know the gas is more dense than the air because it's going down. And not all gases are more dense. Let's let that go a little bit. I'm going to move it off to the side. There we go. Put this down for a little bit. Now this time we're going to go to the fire part of it. Now we knew the carbon dioxide went down, so it's more dense, but not all gases are more dense. In fact, carbon dioxide, well actually a lot of times people say what happens if you take a lighter and put it on the dry ice? It would put out the fire. Without oxygen, fire doesn't work. So if I try something, now this, one of my favorite things, this is called flash paper. Flash paper looks like paper. It even feels like paper, but it's not. It's a chemical that burns quickly and completely. So if you add a spark to this, because in order to have combustion or fire, you need three things. You need a fuel, you need oxygen, and you need a spark. Well, this is the fuel. Where's the oxygen? Yeah, it's in the air. The spark, we're going to use this. If you add all of them together, you get combustion or fire. So take that. Do you guys want to see that again? I do. Hold on. We'll take another piece of flash paper, hold it out here, and again, you have our fuel. Now, flash paper looks like paper and it feels like paper, but it's not. It's a chemical that burns quickly and completely. It might be a little loud because the bubbles in there are a little loud. So if I take it, now very important, you don't want to burn things if you don't know what the reaction is going to be. This is a fuel that burns at a very, very low temperature. Other things burn at very, very high temperatures. So let's take that, add it to this again. Burns up really quick. I think I have one more. Hold on. Let's take this one again. And then I'm going to use it in another way. So fuel, oxygen, spark. Take that. Nice. If I trap it in a container, I'm going to take this. I'm even going to come over here and shut the lights of the office for a moment of our mad science lab. At least we'll get a little dark. There we go. Now, we said there were three things that were needed in order to have combustion. You need a fuel, oxygen, and a spark. So the fuel I'm going to use, fairly safe fuel, burns at a low temperature. I'm going to take ethanol and put it in here. I don't need much. And what I'm going to do, I have the fuel. I want to mix it up with the oxygen. So I'm going to spin it around a little bit. Nice. I'm going to shake it up a little bit. Nice. Let's do that. Now, I don't want to burn the liquid. I only want to burn the gases. So I'm even going to empty out the liquid so that I only have the gases. So we'll flip that around a little bit. Nice. Awesome. Balloon attacking me. Take that, put it down here. I'm going to make sure I'm protected. So I have my goggles and I have my glove. I'm even, so we get the light going a little bit easier. Take a piece of flash paper, put it on the top there. There we go. Let's see what happens when we add it to this. Here we go. Whoops, make sure that's going there. All of a sudden, my lighter doesn't want to work. Yeah, I might have to get another lighter. It should work. Like that. Just worked a second ago. Give me a second. I will be right back. To grab a lighter. Lighter. Awesome. Got another lighter. Not bad doing these things in the lab. Here we go. I'm back. You miss me? Here we go. So you had all these gases in the flame rushing to get out. And what we learned earlier, if you blocked it from coming out, what do you think would happen to the bottle? It would explode. So you never want to trap a gas inside. It can be very, very dangerous, no matter what the gas. Now, this time, we're going to try it another way. Let me try something else. Here we go. Good. Make a quick call. Nice. Lost someone. Good. Now, I'm going to put this aside. I'm going to take these. Now, I need you guys to make a hypothesis or a guess. What do you think is inside these balloons? Most people would say the same thing. Most people will say helium. And why do you say helium? Because the balloons are actually floating. Exactly. So because they're floating, we know there's a gas that's lighter than the air. So what I'm going to do is I'm wondering if I had a spark to this, what would actually happen? So I'm going to move this out more towards the middle. Make sure you can see it there. Good. I'm going to move this one over a lot. Put it over here. we're going to add a spark to this one. Now, if there's helium in the balloon, when we add a spark, all that will happen is the balloon will just pop. Helium is not flammable, so it doesn't catch on fire. We're going to test it. If I touch the string, I'll lose my balloon. So let me put my goggles down. Let me take my glove, put my glove on as soon as I light the candle. There we go. Awesome. And I have 2 of them, so we will do it twice. Here we go. Keep your eye on the balloon. In fact, I'm going to count down from 5. Ready? 5, 4, 3, 2, 1. Add a spark. Now, did the balloon just pop or did it explode? Yeah, it exploded. There was another gas in there. That gas was called hydrogen. Hydrogen is also less dense than the air, so it floats up, but it's flammable. In fact, they used to use hydrogen in blimps. Can somebody tell me, think about it, why is that a bad idea? Well, the Hindenburg, not a good idea, very, very flammable. These balloons can even be set off by a static shock, and they would explode. Now, if I try a different one, in fact, even before I get to it, I'm going to put this down. I kind of want to look at my bucket because it is getting so cold in there. If I reach inside, I can actually hold it now because the ice, there's ice surrounding the piece of dry ice. When you put water in the freezer, it takes about, I would say, 2 to 3 hours before you get ice. And here, it happens in about 10 minutes. Now, eventually that ice will melt on the outside and then I can't touch it. But if I break it, let's see if I actually can, I can actually take out the dry ice that's inside. It's a big chunk in there. I'm going to put this down over here. Now this time I'm going to take my other balloon, and this one's a little bigger, so we'll put it over here. Now again, you can make your guess. Does it have helium? Does it have hydrogen? They're both floating, so that kind of eliminates other gases. If I put carbon dioxide in the balloon, what would the balloon do? Since carbon dioxide is heavier, the balloon would actually go down. When you blow up a balloon, you're filling up with carbon dioxide, and that balloon will always go down unless the wind catches it, but it goes down. These will always go up. I'm even going to lower it a little bit so you can see it there. Nice. So it'll always go up. Now let's see what happens if I add another one, add a spark to this one. I'm going to move away again. Keep your eye on the balloon. Don't take your eye off of it. I'm going to step back a little so I don't have to be so close. Let's light the candle. Oops, wrong one. Take this one. There we go. Do that. Keep your eye on the balloon. Let me make sure I'm protected. Glove on, goggles on. This time I need you guys to count down as loud as you can. I want your room to shake. Ready? Count down. 5, 4, 3, 2, 1. Add the spark. I even knocked down things that were on the desk over there, which is awesome. Now, again, very important. We never play with fire. These things are dry as pop. These things can be very dangerous if you don't know what you're doing. We've always had to make sure we know exactly that they're going to be safe for us and they would be safe for our audience, especially when we're doing live shows. Now, very important. I hope you guys had a lot of fun today. Thank you for joining me for Mad Science. Thank you for joining me in the Mad Science Lab. I hope you guys have a wonderful day. Enjoy the rest of it. Bye, guys. Have a great day.